So Jai Hind everyone. This is Dr. Avdhesh Gupta, Professor, Department of Information Technology, Ajay Kumar Garg Engineering College. So in the previous lectures, we have discussed about IPv4 addresses, IPv4 classless and classful addresses. So today we will discuss about IPv4 and IPv6 header datagram. Okay. So what is IPv4? We have already discussed that IPv4 is a 32-bit IP address, 32-bit logical address, and it is basically an internet protocol version 4, and it is basically used for delivery mechanism used by TCP/IP protocol. The main important thing is IP protocol is a connectionless and unreliable protocol. This is the reason we are keeping IP internet protocol with TCP, because TCP is a connection oriented and a reliable protocol. That's why we are using both protocol along with. Okay. So keep in mind that IP is a connectionless and unreliable protocol, while TCP is a connection oriented and a reliable protocol. Okay. So where this IP or IP exists, basically IP exists at network layer. You can see it in the TCP/IP model that these two are the physical layer and data link layer. This is the network layer. There are various protocols exist at network layer like IGMP, Internet Group Message Protocol, ICMP, Internet Control Message Protocol, IPv4 or IPv6. This is the logical addresses. IPv4 is a 32-bit address, while IPv6 is a 128-bit address. ARP, RARP, boot and many more protocols exist at this layer. So we will discuss about IPv4 or IPv6 protocols datagram format here. Okay. So next layer is a transport layer where SCTP, TCP, UDP, and another layer is application where different protocols are there. So we will discussing on IPv4 and IPv6 exist on network layer. Okay. So IPv4 datagram format. IPv4 datagram format, the total size is minimum 20 bytes and maximum is 65,536 bytes. This is the total size of this IPv4 datagram format, okay, where 20 to 60 bytes, minimum 20 and maximum 60 bytes kept for the header and the rest is for data. Okay. So data size is equals to how much data size we can keep it along with IPv4? Maximum 65,536 minus 20 if header datagram size is 20, or 65,536 minus 60 if the header format is 60 byte long. So this is how we can calculate the data size we are delivering with IPv4. So this is IPv4 header format. The size of IPv4 header format is maximum 65,536 and the minimum is 20. This 20 bytes has been kept for the HLAN, header length. So minimum size of HLAN should be 20 bytes. So therefore data size is 65,506 bytes for data size. Okay. So this is the header format where this is the first 4-bit, this is the 32-bit. Keep in mind that header format is always, even we are studying ARP, RARP, IPv6 and any other data format, all data format is of 32-bit long. So first 4-bit kept for version, next 4-bit kept for HLAN, header length, next 8-bit kept for services, different type of services we are using along with this IPv4. Then the total length is the data size. What is the data size? 16-bit. The identification basically used for the identification of the packet frame. Which type of frame is this, or what is the sequence number of this? Then the flag 3-bit, fragment offset, time to live, protocol, header checksum, source IP and destination IP and option. So we will discuss each and everything in detail. So first field is version. What is version? 4-bit. The version is always, if we are studying about IPv4, the version is 4. This is 4. So what we are keeping here, this 4 is treated as 0100. This is 4. So we can say that this is IP version 4. So this is fixed for this 4-bit. If this version field has another bit except this, so we can say that this is a corrupted frame. We cannot accept this frame as a IPv4 header datagram. Okay, so this is fixed. So next is HLN. HLN is minimum 20 bytes. HLN is minimum 20 bytes. So minimum 20 bytes, what does it mean? It means HLN should be minimum 20. So it means 1010. Sorry, this is 10. So to make it 20, this is 20. So 20 means 20 bytes. This is bits. So to convert it into bytes, we have to multiply it by 4. So if the HLN is, for example, 0101. So this is we are reading is as 5. So what is the header size? Header size is 5 multiply 4. It is 20. So this should be the minimum size of HLN. So HLN should be minimum 5, or we can say 0101. If it is less than this, then the frame is again corrupted. We cannot accept the corrupted frame to deliver the further. Okay. If the HLN is more than it, suppose HLN is, we are keeping this HLN is 110. So what is this? This is 6. 6 multiply 4 is 24. So the size of HLN is 24, but the minimum size is 20 bytes for header. So we are keeping 20 bytes for header and 4 bytes kept for the option field. 4 byte for option field. So 20 bytes header and 4 byte option field. The option field size can be calculated as, if the header size is more than 20 bits, so we are subtracting 20 from the header length. So the rest is the option size. So maximum header length is for 60 bytes. So minimum 20 and header option size is 40 bytes maximum. So next is the services. The services and other field we will discuss in later slides. Okay. So this is all about the services and differentiate services. In the services, this is of 8-bit. So first 3 bit are unused. We are not using these 3 bit, and the last bit is also treated as unused bit. Yes. In today's scenario, if we are using IPv4, we are not using this type of services because this is obsoletely finished and merged with another. So if we are using IPv4, then in previous version, IPv4 version, in few years back, we are using this. So this is for precedence bit. Precedence bit is always kept as blank or 0. The next 4 bit is the TOS bit, and the last bit is also unused bit. So the symbolic representation of these 4 bits is a DTRC. D for minimize delay, R for maximize reliability, T for maximize throughput, and C for minimize cost. So if D bit is 1, so what we understand that this particular frame, this particular data is for minimize the delay. It should be delivered as soon as possible. If we are keeping in the D and T, both are 1. So minimize delay and maximize reliability. If all bits are 1, then we are using minimize delay, maximize reliability, maximize throughput, and minimize cost. But listen one thing. Can we have the minimize cost and maximize throughput and minimize delay? No. So minimize cost, if we are keeping it as C as a 1, so other should be 0. Because if we are keeping as minimize cost, so it means everything is 0. We are keeping is minimized cost, so reliability doesn't matter, throughput doesn't matter. Minimized delay, yes, it can be one option, but if C is 1, then other bits are 0. But if D is 1, we can keep it maximize reliability as 1, delay minimum, but reliability also 1. Okay. And this is a differentiated services. So in later slide, we will discuss about the differentiated services. In the differentiated services, last 2 bit is unused. So first 5 bit is in use, 3, 3, 6. 6 bit is in use. Okay. So the precedence subfield was part of version v4 but never used. We have already discussed that this 3 bits we are not using. So this is the type of services. If all bits are zeros, then it is a normal or default. If DTRC, C is 1, then minimized cost. R is 1, then maximize reliability. T is 1, then maximize throughput. D is 1, then minimize delay. What are the protocol we are using at these different US bits? These are zeros. ICMP, Internet Control Message Protocol, all zeros. BOOTP protocol, Bootstrap protocol, all zeros. Normal, DNS, TCP query. So these all we are using if all bits are zeros. If C is 1, then minimize cost, then we are using NNTP protocol. If R is 1, maximize reliability, then IGP or SNMP is used. If this is 1, minimize the delay, then Telnet is used. Immediately delivery of the packet to the next machine. If T is 1, then maximize throughput, then FTP. So these are the different protocol. If we are keeping any bit 1, DTRC, so we are using these different protocols. Okay. So these are the different code point, a simple code point for the differentiated services. 6 bit, later 2 bits we are not using. If the value is 1, then we are using ICMP protocol. If value is 2, then IGP protocol. If that is 6, then TCP protocol. 17, then UDP. 89, then OSPF. And what about others? 3, 4, 5, 7, 8, 9, 10 and others. There are lots of protocols are there. Very few of them we are not using. These are the most common protocol we are using. Other are also we are using. But these are the most common protocol that we can learn. We can write if in any examination it can be asked that what are the various protocol we are using at differentiated services. So we can remind that these are the 5 well-known protocol we are using at differentiated services. Okay. So the total length. Next field is total length. The total length defines the total length of datagram including the header. So to calculate the data, we have to subtract the header size from this. Okay. So length is 46 byte. Data should be less than 46 byte with padding, and we are keeping it a padding. If the data is less than 46, then the padding is used to make it data is 46 byte. Many questions has been arised that why this 46? If we are keeping it as a minimum size 20 bits, 20 bytes or 30 bytes or 10 bytes, is there any use to deliver the data separately? Okay. You said that there is a size of data, so that a few size of data, a lot of size of data has been delivered with packet 1, and for second packet there is only 10 byte of data. So 10 bytes of data make it sense to deliver from source to destination? You can say yes, but the limitation of the internet or limitation of transmission media or transmission TCP or IP is that the data should be of minimum 46 bytes, because we are following some standard protocol like IEEE 802.3. In IEEE 802.3, we are keeping its minimum 64 bytes. So in here we are keeping is 46 byte. So this is must to keep it as a standard size, that minimum 46 byte is there, and if the data size is 46 byte or more than 46 byte, then there is no use of padding. The padding is used to just to make it the minimum data length. Okay. So next is different protocols. ICMP, IGMP, OSPF, TCP, SCTP, UDP. These are the protocol we are using with IPv4. You are saying that these are the protocols we are using at transport layer. Yes, we are using these protocol at transport layer, but we are defining that we will use these protocol at transport layer. What is the responsibility of network layer? It is the responsibility of network layer to decide which type of protocol we are using at other layer also, upper layer. Okay. So these are the values we have already discussed. One ICMP, IGMP, TCP, UDP and OSPF at different values. So now comes on few examples, like an IPv4 packet has arrived with the first 8-bit as this. If it is in binary, then it is good. If it is in hex, then we keep it a different format. So we will discuss this later. So the receiver discard the packet. Receiver is not accepting this type of packet. Why? What is the reason behind it? Let's see the solution. In this packet, the 4 leftmost bit is 0100, 0100. So this is IPv4. This packet belongs to IPv4. So there is no mistake. What about the other 4 bit? 0010. It make it 2 multiplied by 4, it make it 8. So next field after the version field is HLAN. What is the size of HLAN? Minimum size is 20 bytes. If it is less than 20 bytes, the frame is corrupted. We cannot accept the frame. If it is larger than 20 bytes, then the rest byte kept with option field. The maximum HLAN size should be 60 bytes. Okay. So the next bit is this. So the invalid header format is 8. The minimum number of bytes in the header is 20. The packet has been corrupted in transmission. So that's why the receiver reject this frame. Okay. So next example. In an IPv4 data format, the value of HLAN is 1000 in binary. So how many bytes of option are being carried out by this packet? 1000, it is 8. 8 multiply 4, it is 32. It is 32. So 20 bytes kept for HLAN and the rest 12 bit kept for option field. So this is the solution. The HLAN value is 8. The total number of bytes in header is 8 multiply 4, 32 bytes. The first 20 bytes are the base header and the rest 12 bytes as a option field, the size of option field. Okay. So next example. If an IP packet, the value of HLAN is 5 and the total length field is 0 cross 028. So this is the representation for hexadecimal representation. Hexadecimal value is represented as 0 cross and the hex number. How many bytes of data being carried out by this packet? HLAN is 5, so it is fixed that 5 multiply 4. So we are keeping this HLAN is 5 multiply 4, it means 20 bytes. So there is no option. वहां पर कोई option नहीं है. Now this is 0 cross 0028. What does it mean? If we are converting this into decimal number, so how can we convert it? 8 multiply 16 to the power 0 plus 2 multiply 16 to the power 1. It means 32 plus 8, it means 40. So this 40 is a size of 16 plus 16 to 30 plus 8, 40. 40 is the size of total length. Total length size of 40. So we have to subtract 40 is the size of total length including the header size. Header size is given as 20 bytes. The question asked that how many bytes of data is being carried out. So we have to subtract -20 as HLAN from the total size of 20 bytes is the size of data. Okay, so 20 bytes is the header size HLAN, and 20 bytes for the data size, and the total length is 40 bytes. Okay, so next example. IPv4 packet has arrived with the first few hexadecimal digit as shown is this. Okay, how many hops can this packet travel before being dropped? Now keep in mind that if we are not remembering, we are not making the header format, so we cannot solve these type of questions. So it is very must to keep in mind or draw the rough header length format every on the page where we are solving these type of question, so that we can understand which type of number has came into which field. Okay, so how can you imagine that, how can you calculate that how many hops in the packet travel before it dropped, means what is the time to live for a particular packet. Okay, so we can keep it as just as checking the previous slides. Version HLAN services total length. Okay, identification flags and fragment we have skipped it, we will study later in the sense of after this question. Time to live, this 8-bit, time to live 8-bit. It comes after how many bits or bytes? This is 32 bits. This is 32 bits. It means after 64 bits, the time to live field has came after 32 bit. So how many hex digit? Because the question given in hex digit. How many hex digit? Hex digit, one hex digit is equals to 4 bits. One hex digit. So how many hex digit we have to pass to calculate the time to live? The question is in hex digit, na? So how many hex digit we have to pass? How many hex digit? 1, 2, 2, 4 and 4, 8. It means total 1, 2, 3, 4 and 4, 8, yani ki 16 bit. We have to pass 16 hex digit to calculate the time to live. So next now comes to that particular question, so that we can pass the first 16 hex digit to calculate the time to live for this particular frame. Okay, this is not the question. This we have already done. This we have already done. Yes, this. So we have to pass first 16 hex digit. Which one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Up to this 0. So only 0, 1, 0, 2. The next field is 0, 1, 0, 2. Okay. 0, 1, 0, 2. The first 16 hex digits we have passed. Okay. So how many hops? 0, 1. 8-bit 0, 1. If we are converting into decimal or in another format, it will be the 1. So we are passing only one hop. Hop is called one router we have to pass to reach its final destination. Okay. So this is the solution. To find the time to live, we skip 8 bytes, or we can say we have skipped 16 hex digit, and the time to live field is 9th byte, which is a 0, 1. This means the packet can travel only one hop. The protocol field is next is 0, 2. This is a protocol field. So the protocol number is IGMP. We have already discussed in previous that 1 is what, 2 is what, 8 is what, 16 and 49 is what. We have already discussed. So this is you all have to remember. Now comes on maximize transfer unit MTU, IP datagram. The maximum length of data to be encapsulated in a frame. This is IP datagram. So how can we calculate this MTU? We can calculate it by using these different types of protocol. If we are using hyper channel, then the MTU size should be 65,535. If this is token ring, 16 Mbps speed, then the MTU size is 17,914. And the token ring 4 Mbps, then 4464. FDDI for this is 4352, Ethernet 1500, X.25 576, and EEP 296. Currently we are using in our daily life. This is Ethernet, FDDI, token ring 4-bit 4 Mbps and token ring 16 Mbps. Okay. So the next field is, this is unused 3-bit. So first field is unused D and M. D for do not fragment, M for more fragment. We will discuss various examples along with this. So this is the fragment example, fragment offset. This is the byte 0000 and the byte is 3999. So offset is always divided by 8 because this is the size of 8-bit. We can treat that 8 bits in a byte. So the first is, if the size is 3999, so we have to divide 0000. The total size is already given, that is 1400. The size of this particular frame should be 1400. This is given in the question. So we have to keep it 000 to 1399. What is the offset? 0000 divided by it gives 0. So this is the fragment identification number. This is 1400, start from 1400 to 2799. Then the offset is 1400 divided by 175. And then after this 2800 to 3999. It is a lesser than 1400. So because we have already this type of data, so we are dividing 2800 divided by it is 350. Okay. Like for example, this is okay. This is do not use, do not fragment and more fragment, identification, fragment offset. Okay. The size is this. So we can keeping this 1400, 20 is the header size, HLN. HLN is 20. So data is total 1400 bytes of data, 20 bytes for header length, and 000 is 000 divided by 8. So we are keeping is there 8. 14567 is the sequence number for this identification for this protocol. Okay. So these are the bytes. This fragment 1. Then comes on fragment second. Fragment second is 1400 2799. This is fragment 2. And this is fragment 3, 175 and 350. Already we have discussed in 175 and 350. We have already discussed. So 175 and 350. This size is 1420, rest is 1220. 20 bytes for header length. Okay. So if we are dividing this fragment into 2 fragment also, this is just for if there is a congestion in communication media, or we have to divide the packet size into some smaller size. So we can do it. So how we can do it? 1400 to 2799. So 1400 to this is 820. The size of this is 800 and this is 600. 24 header length. So 800 and 600. So 14000 to 2199 and 2200 to 2799. What is the fragment offset? We can always calculate the fragment offset by the first starting number divided by 8. 1400 divided by 8, it gives 175, and 2200 divided by 8, it gives 275. So we can keep it as. Okay. So this is all about the fragment and fragment offset. Next question is about the 3-bit. First bit unused, do not fragment and more fragment. If the packet has arrived with the M-bit value of 0, is this the first fragment, the last fragment, or a middle fragment? Do we know the packet was fragment or not? Let's see. Just before it, this is D and M. M is 1. This is unused. This is a D. D, do not fragment more, and this M for more fragments are there. More fragments are there, it means there are multiple offsets are there, there are more fragment, more fragment, more fragment. So M bit is 0, M bit, the last bit is 0, it means that there is no further fragment. So this can be the last fragment if M bit is 1, M bit is 0, because there is no further fragment, more fragment. So this is the last fragment, but it can be first fragment also. It can be first fragment because we do not know that the particular fragment is fragmented or not. Maybe the packet is not fragmented. So this can be a first fragment or the last fragment, but it is not the middle fragment. Okay. So if this is 0, then it means there is no more fragment. It can be last. However, we cannot say that the original packet was fragmented or not. A non-fragmented packet considered the last fragment. So we can say that this is the last fragment. first fragment, we cannot say that this is fragmented or not. So, if this is fragmented from the previous one, then we cannot say this is a fragment, because if we are keeping it in this example, in this is fragmented, but this is not fragmented. This cannot be the first fragment. This is the first fragment, but this cannot be the first fragment. Okay. So, this is further not divided, but this is not the first fragment. This is the last, but this is not the first. Okay. So, in this case, but if we talk about this, this is the first and last also, if we are not dividing this far. Okay. So, next question. A packet has arrived with the ambit is 1. Is this the first fragment, last fragment, or middle fragment? More fragment. It means there at least some more fragments are there. At least one fragment is there. So, this is not the last fragment. This can be in middle. बीच में कोई भी हो सकता है, फर्स्ट भी हो सकता है, फर्स्ट के बाद और भी हो सकते हैं. तो दिस कैन बी द फर्स्ट फ्रैगमेंट और द मिडिल फ्रैगमेंट, बट इट इज नॉट द लास्ट फ्रैगमेंट. Okay. Next example, packet is with ambit with 1 and the fragment offset value is 0. If this is the first fragment, yes. If fragment offset value is this, then it is the first fragment. Very simple. Packet arrived in which the offset value is 100. What is the number of first byte? Do we know the number of last byte? We multiply the offset by 8. 100 multiplied by 8, 800. So, we cannot determine the number of last byte unless we know the length. If the length is given, so we can say that from 800 to this one. Okay. So, this we have already discussed. If hash line is 5 and the total length field is 100, what is the number of first byte and the last byte? 800, 100, then header length is 20, this is minimum. So, we can say that 80 bytes in the datagram and first byte is 800 and the last number will be 879. Okay, because 80 bytes are kept with the datagram. So, we can say in this case the last number of this particular frame is just 800 to 879. Okay. So, this is the checksum, we will discuss this later. So, today we have studied about IPv4 header diagram. So, we can skip some portion, we will cover in next video lecture. Okay. So, thank you very much.